Hello class, this is Professor Finan. In today's lecture, we will cover our final goodness of fit test, which is called bootstraps or bootstrapping, which is also known as residual resampling. And so we're just going to go over the bootstrap procedure. But first, we found that in our residual analysis that there's the actual data points, and then there are the residuals. The residuals by themselves contains a lot of useful information in terms of assessing our goodness of fit, and we already experienced that in the graphical residual analysis. And so the bootstrap procedure is a way to extract more information from the residuals. And so let's just go over the procedure quickly. And so the first is, just like the jackknife is, you perform the regression on the data set containing your M samples. Then you will, like we always do, you calculate the residuals in the normal way. So the ith residual equals yi, the data point, minus the regression function, the regression model evaluated at input xi. And so now you have a vector of residuals. Okay, you have your n residuals, and you already have built that vector in order to make your residual plot. And so now, in bootstrapping, is what you do is these residuals are ordered. They are corresponding to each xi. And so with bootstrapping, what you do is you randomize the residual vector. So basically you rearrange the order of the residuals. So I'm going to call it our residual vector R with subscript R, meaning randomized. And so now we're still going to have, n residuals, but now you've basically, you've rearranged the residual vector. And so now we're going to define some new data points, and then we are going to call these bootstrap samples. And so the output y with subscript bi, meaning bootstrap. So the ith bootstrap output equals the function, the regression model evaluated xi, but now you're adding the ith residual. And so now the actual value of the residual, the ith residual, it might actually be R2 from your actual true residual vector, or it might be Rn or n-1. And so you're adding, this residual actually came from the data set, but now you're adding it to the regression model evaluated at a different input location. But also through the randomization process, it might actually be the original, it could be the original residual. And so now we have a new data set, the YBI, the bootstrap output with each input sample. And so now we will perform regression on the bootstrap samples, and then you record your new coefficient values and your other parameters like R squared, and also your residual sum of squares and things like that. And then you will repeat, just like in jackknifing, you can repeat step 4 and 5 many times. In fact, you could do if you want to, you can do all possible permutations of your original residual vector. And one of the advantages, and once again, this is probably more useful if you have a small data set or when it's prohibitive to do cross-validation. And so generally, if you can collect more data, cross-validation is the much more robust procedure. But this is, so the jackknifing and bootstrapping is usually done when your data set is limited or finite. And the advantage of this is all of the data are used. So with jackknifing, we're still actually leaving out one of the data points. And so, and some of the possible disadvantages is that the original regression can be influenced by the outliers. And so this regression model, it might be heavily influenced by a data point with high influence, or also any outliers. Okay, so this is sort of showing you what we mean by randomizing the residual vector. You basically, so in this case, in this example, the first residual was moved to the nth location. The Rn went to Ri went to the first position, and then in this case, the residual 2 is actually still the same the true residual. And if you're using MATLAB, you can do the permutation yourself, but also like in MATLAB, there's the randperm function, and it just does a quick random permutation. Okay, so here's like a sample. I use usually EPS for my, that's for random. In this case, if our variable EPS happens to be our residual values, and so that's just some example coding there. Okay, so let's look at an example of bootstrapping. So this is our 25 points from 1.5 x sample case. And what we've done is we've done the bootstrapping. We fit basically, I guess, 25 additional models. And so we have 25 here lines of best fit. One thing to remember though, because the actual residuals sum to 0, and so the sample mean of the bootstrap samples is identical to the original dataset sample mean. And remember, with a simple linear model, you're constrained to pass through the line of best fit is constrained to pass through through that sample mean point. And so all 25 of these bootstrap regressions pass through the sample mean of the data. And then here's the actual plot. This is the slope beta 1 and the y-intercept beta 0. And this green square is the exact 1.5 and 0. And so you see, you do get this spread of slope values from about 1.65 down to about 1.25 based on your bootstrap samples. And the y-intercept from about positive 0.1 to about negative 0.1. See how all of these combinations of y-intercept and slope, they're actually on a straight line? That's because in a simple linear model, you're constrained to pass through the sample mean. And so there's a direct correlation between the slope and the y-intercept due to the constraint that the fit must pass through the sample mean. Now let's look at, when we have the 5 data points. So here we've done 5, I believe 5 boost. No, there's more. There's actually more. It's I think 5 factorial. There's maybe we have all the permutations here. So maybe it's about 20 or 30 lines of best fit. Okay, and so with this data set, once again, we get different combinations. But the point here, all of the lines of best fit must pass through the sample mean. And what's interesting though, some bootstrap samples will give really similar to your original data set coefficient. Okay, this is probably the more interesting case. This is our 10 points from the sine example problem. So this is the original regression with a cubic fit. We're doing a cubic fit. So these are all the permutations of these 10 residuals. One thing to notice, there is a certain permutation where, for example, this data point here would probably has the largest random noise, or the largest positive residual. And probably this data point here has the largest negative residual, or a residual with negative assignment with the largest magnitude. So there is a permutation where this data point would receive this negative residual, and then this data point we see the positive residual, and so the data points might be paired. There is one permutation where basically, that's actually this line here, there is a line that's going to be very, very flat. Not exactly flat, but it's where are certain combinations where all of the data points with negative sign residuals are now paired with a positive sign residual and vice versa. And that will tend to like flatten. But you can kind of see that almost all of these are sort of still following a general sign shape. But what this tells you is, so if you look at sort of the thickness, this kind of gives you, it's almost like it just shows you the variation. It gives you a physical interpretation of, there's noise in the data, and so your fitted regression model is not going to be perfect. It just kind of gives you the amount of the variety of possible fits that might be okay. And then just like in the jackknife example, you can plot the different combinations of coefficient values. And here just we see there's actually for coefficient 3 and coefficient 1, so this was a cubic, so this is the first beta 1 and beta 2. There's this really direct correlation, and between coefficient 2 and coefficient 4, so the third order term. Oh no, this is the 3 and 1. So this is the beta 2 and beta naught. There's actually a really strong correlation. And then 2 and 4, which is beta 1 and beta 3, there sort of is also a correlation. Where some of the other combinations are more of a random spread. So for your homework assignment, you can do for the sign problem with the 25 data points, you can basically remake this plot and this plot, but using the 25 data point data set. But generally, both the jackknife and Bootstrap, it's when your data set is limited, you can start to gain some additional information. But generally, I personally will just do the cross-validation.